Hello, welcome back. Today we look into an important concept which is called transfer function. Uh, I'm going to be saying this term quite a lot in this course. You can also find more information about this in your reference book NIST chapter 2.3. So let's see how it is defined. Transfer function of a linear system is defined as a ratio of Laplace transform of output variable to Laplace transform of the input variable when all initial conditions are zero. So when you read this definition, there are quite a few uh, terms that you may think are new and you may wonder about it. Linear system, output variable, input variable. To understand this, let's try to consider an example that is quite often seen in textbooks in mechanical engineering. So let's consider a mass which is connected to a wall through a spring. So the spring has a spring constant of K and the mass is this of M. Let's assume we're applying a force Ft, and as a result we end up getting some displacement which is given by xt. In this case, you may remember from your previous classes like Mech-Eng 222 that we can find out the equation of motion. The equation of motion is given by m second derivative of displacement plus k times x is equal to ft. Also, we know that generally we apply some kind of a force, we give the mass a push, and that's why we end up getting a response of the system, which is the displacement. So we understand from intuition and from experience that usually force is some kind of an input function, an input variable. You can apply different kind of forces, and as a result you will end up getting some kind of an output response, which is the displacement in this case. So the system is the physical setting. The input variable is the force over here, and the output is the displacement. In general, we are able to come up with differential equation representations for most dynamical systems. So, as an example, let's say if we have a differential equation which is given by what is shown over here. Here R is the input and Y is the output. And we have a differential equation which is given as second derivative of y plus 7 times derivative of y plus 3y is equal to 2 times the input variable r. If you are trying to find out the transfer function, so the first step will be to take the Laplace transform of this equation. In order to take the Laplace transform, we can, as we described, that r is some variable that we have defined in the time domain. If we take a Laplace transform, we can assume that it is represented by a capital R in the Laplace domain. Y similarly will be given by capital Ys. Derivative of y can be described in terms of the Laplace of y. So it will be Ys minus y0. Here we know that since we are taking the transfer function over here, so by definition all initial conditions are supposed to be zero. So this will be assumed to be zero. Similarly, the second derivative of y, if we find out the Laplace transform, will be, the derivative of y will be s times ys minus y0. The second derivative of y will be s squared times ys minus y dot 0 minus s times y0. So again, these initial conditions, which are y and derivative of y at 0, will be taken as all will be taken as 0. So if we replace that, we can write down the equation as uh, s square ys plus 7s ys plus 3ys is equal to 2 times rs. We can collect the y as a function of s terms and r as a function of s terms on left hand side and right hand side, cross multiply, and end up getting a transfer function over here. Here you can see, because of the nature of the differential equation, since numerator is basically coming up with the coefficients of the r, the denominator is coming up with whatever were the coefficients of ys in the left hand side. We end up getting a transfer function which in general can be represented by some numerator which is a polynomial of s and some denominator which is a polynomial of s. So as I mentioned, the numerator is a polynomial function of s, where the highest power of s in this expression is assumed to be m. The denominator has the highest power, where the highest power of s is n. And in general, for most dynamical systems that we will study, we will notice that m is less than or equal to n. If we look at this transfer function and we equate the denominator to be 0, so we take ds and equate it to 0. In this case, it will be an s to the power n plus an minus 1 s to the power n minus 1 all the way to a0 equated to 0. This equation is referred as the characteristic equation. As the name implies, the equation describes a few important properties of the system. And it's quite important to, seeing the form of this equation can be quite important to understanding how the systems will respond. If we solve the roots of this equation, we'll end up getting the roots of this equation are often denoted in this text by pi, which are also referred as the poles of the system. So we used this notation earlier also. So they are referred as poles of the system. Similarly, if we equate the numerator to be 0 and solve for the roots, so the roots of this equation will be denoted by zi, and here zi are referred as zeros of the system, also called because these are the values. If I replace s with the 0, then my transfer function gs will become 0. If I graphically represent them, so in general, both poles and zeros are going to be complex numbers. If I graphically represent them on a pole zero map, on a complex plane, a complex plane is basically where the real axis, where the horizontal axis is describing the real part of a number, and the vertical axis is showing the imaginary part of the number. So here, each number will just be a point. So I represent the poles by x and the zeros by an O. So if I show them on a pole zero map, if I show them on the complex plane, I end up getting what is a pole zero map. As an example, this transfer function is s minus 2 over s into s squared plus 2s plus 5. The highest power of s in the numerator is 1. So it has 1 0, which is located at 2. The highest power of s in the denominator is 3. We can see the roots are 0, and then the roots of the quadratic term, which are a complex conjugate pair. So we end up getting 3 poles. So if I represent them on the complex plane, the 0 is at 2, and the poles are at 0, and a complex conjugate pair, which is at -1 plus minus 2j. So I have 3 cross. This will be the pole zero map. This pole zero map is quite an important representation to understand system response. For example, with my experience of Mechanism 322, I can tell that this system is a marginally stable system. So it will respond and settle down for some inputs, but it may increase to infinity for the response may increase to infinite values for other kinds of inputs. I can also tell that this system uh, has a mode which is going to oscillate for some time before settling down to some constant value because of the poles at complex conjugate pairs. By looking at a zero on the right half plane, I can also say that when I apply some input, the response will start off in the opposite magnitude direction because of this zero, which is in the right half of the complex plane and referred as a non-minimal phase zero. So these are some of the things that you will also be able to tell after you go through a few lectures in this course. Okay, so for the system, for the physical system that we were starting off with, the mass spring damper system, which we investigated in the start of this lecture, let's consider it again for a while. So let's consider that we have a system. So the system that we had, here, if I applied an input, I can graphically represent that I apply an input, which is some forcing function, and the output ends up being the displacement. So the resulting is the arrow coming out, which is the displacement xt. So this is just a graphical representation. This kind of a graphical representation is also common in this course. And what we can do is that we have an input where my input is shown by either US or UT. The system is represented in a block by the transfer function GS, and the output that I'm getting is YS or YT. Notice that in the time domain, describing how X depends on F is coming through the differential equation that we described. And there is no easy way of describing what an X is for a particular value of F without solving that differential equation. But in the Laplace domain, I described that GS is equal to YS divided by US. So since Laplace transforms, the differential equations are just algebraic equations. So I can describe that in the Laplace domain, Ys is just equal to Gs times Us. So it is easy to find what is the output Laplace transform of a system if I know what is the input acting on the system and if I know what is the transfer function of the system. And this is a very important benefit of working with Laplace transforms in order to analyze systems for the purpose of control systems. So let's try to see this through the next example, which is just going to do a little bit of calculations to find out what is the response for a particular transfer function. So this example is asking to find what is the time response from a system, yt, which has a transfer function gs for an input unit step input ut. So unit step input, remember, is basically just a value of 1 after time t is equal to 0. And also recall that the Laplace transform of the unit step function is just 1 over s. So we need to plot yt and show the pole zero map. Pole zero map just comes from the transfer function. So let's start with the pole zero map. Here we can see that GS has a 0. So the numerator has an order 1. So we can see that it has just 1 0. And that is given by equating the numerator to writing an equation 2s plus 1 is equal to 0 and solving it. So we end up getting the 0 as negative half. Poles can be found by looking at the denominator equal to 0. So here, poles, which are p12, can be found as roots of the denominator, which in this case are negative 2 and negative 3. So the transfer function gs can also be written as 2s plus 1 over s plus 2 into s plus 3. So if I show them on a complex plane, my 0 will be represented by an O at negative half. The poles will be represented by cross symbols at negative 2 and negative 3. So I end up getting the pole 0 back. If I'm trying to find out the response yt, so first of all, let's start by determining what is the let's start by determining what is the Laplace transform of y. So that is found as what is shown in the top of the page. So we can find out ys is equal to gs times us, which is equal to 2s plus 1 s plus 2 into s plus 3 times the Laplace transform of the unit step function, which is 1 divided by s. So we can expand this as a partial fraction expansion, which gives three terms: k1 divided by s plus k2 divided by s plus 2 plus k3 divided by s plus 3. We can solve for k1, k2, k3 using cover-up rule. I'll let you do that yourself and satisfy yourself that this is equal to 1 over 6 divided by s plus 3 divided by 2 over s plus 2 plus negative 5 divided by 3 over s plus 3. We can find out the inverse Laplace transform to find out yt. So the first one is just the inverse Laplace transform of 1 over s, which is the step function. So we just multiply it with the coefficient. So 1 over x times 1 plus 3 divided by 2 over inverse Laplace transform of 1 over s plus 2. So this can be found by looking at the inverse Laplace transform of 1 over s plus a, which is exponential function, e to the power minus 2t. And the third term similarly will be 5 divided by 3 into e to the power minus 3t. You may be interested in seeing some of the, so you can see that this response corresponds of a constant value plus 2 exponential terms. And you can also see that as my time is increasing, these exponential terms are going to go down to 0. So what I'm going to be left up with is just 1 over 6. So this 1 over 6 is also referred as the steady state value. And we can denote it by YSS, which is also written as limit s tending towards 0, limit t tending towards infinity of yt. So if we try to sketch this response, we can see that the response is going to basically look something like y. So st increases, we will end up being at 1 divided by 6, and we have two exponential terms. So basically these are going to decay over time, but one has a positive quotient, the other has a negative quotient. So uh, one has a half, the other one has a quotient of 5 divided by 3. So we may have some transients where we uh, approach the steady state value through exponential terms and decay down finally at 1 over 6 and remain at 1 over 6. In this problem, it was asked to plot the response yt. So it was reasonable to find out what the time response yt looks like. But another way of stating the problem would also be that instead of sketching this yt plot, I just ask for what is the steady state value of y. In which case, remember, in this case, you may like to remember that there is a property of Laplace transforms which describes what is the limit of a function as t tends towards infinity by looking at the Laplace transform. So this can be found just by taking limit s tending towards 0, s times fs. So if we were trying to find out the steady state value, we could also find it by the Laplace transform of ys using the final value theorem. We could find yss is also equal to limit s tending towards 0, s times ys, where ys was calculated before. So it is basically limit s tending towards 0, s times 2s plus 1 over s square plus 5s plus 6 times s. So one of the s in the denominator cancels with the s in the numerator, and we just end up getting the rest of the term by substituting s is equal to 0 as 1 divided by 6. So that finishes the flipped lecture for today. Thanks for paying attention. See you very soon again.